Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level puzzle. And take that easiness with a grain of salt because it's considered easy by the people on the Logic Masters Germany forum, and there's a lot of really smart people there. Today's puzzle is called Positive Negativity 5 by the Bard, and here are the rules. We have normal Sudoku rules apply, which means place the digits 1 through 9 in each row, column, and box. We have yin-yang shading, where we need to shade some cells so that all shaded cells and unshaded cells form two orthogonally connected areas, such that no 2x2 area is entirely shaded or unshaded. That's interesting. And all the digit values in the shaded area are negative values for all clues. So this is an example of a valid yin-yang shading because all the shaded cells are orthogonally connected to each other, and all the unshaded cells are orthogonally connected to each other. And what does it mean for orthogonally connected, for them to be orthogonally connected? It means that in one, if you have a cell in the shaded region, you can get from that cell to any other cell in the shaded region just by going through edges, all while staying within the shaded region. So for example, to get from here to here, you can just go all the way around here, all going through edges, all while staying within the shaded region. This would not be a valid yin-yang shading, because to get from, assuming this was shaded, because to get from the unshaded region to any other cell in the unshaded region, if you try to go from here to here, you would have to either go through the shaded region or go through a corner, which is not allowed. Also, you cannot have this be a valid shading because you have a 2x2 area here, which is all unshaded. Similarly, you can't have this be a valid shading, even if this one is set, because you have the 2x2 area here, which is all shaded. And for purposes of values, a shaded cell is negative. And that's important because of killer cages, where values in cages add up to the total in the corner, and digits may not repeat in a cage. But values, well, values can't either, because they would have to have negative value or positive value, and the digits preclude essentially having the same values, right? So digits cannot repeat it with a cage, and because of that, we know you can't have the same values in a cage either. And those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. So if we have any two-digit number, which adds up to... Sorry, if we have any two cells which add up to a two-digit number, we know those have to be both the same value. Both the same shading. And if they're positive, they're both unshaded. If it's negative, that means they're both negative. So these are both unshaded and these are both shaded. 23 is interesting. Oh. Any 2x2 box has to have at least one of the other shading. So if it's a 23 box, that means you have to have 3 that are unshaded and 1 that's shaded. And this must be 7, 8, 9 as the unshaded, and then 1 as the shaded to add up to 23, right? Because 7, 8, and 9 added positive is 24, minus 1 is 23. So this is negative 23 here. So this has to have 3 cells that are unshaded and 1 cell that's shaded. So this is, again, 1, 7, 8, 9. We don't know where the 1 is. But we do know at least one of these two must be shaded. Because, okay, and we have 2 by 2 that's all unshaded here. So this must be shaded here. We know one of these is shaded. For yin-yang shading, once you swap twice, you cannot swap again. And the reasoning is, so we know this is blue. One of these is blue at least. It could be both. If we try to have a blue shading here, we know this is green. It would swap once, twice, 3 times, and then a 4th time here. But try to orthogonally connect the blue region. If you do, you're going to break apart the green region into not just one orthogonally connected region. That's the reason why you know you can only swap shadings twice on the edge of the grid. I should have said that specifically, yeah, on the edge of the grid. So that means it can swap once from here to here and then once from here to here. That means the rest of the edge must all be green. So this must all be green here. Therefore, this is blue to be the 2 by 2 area. We know one of these is blue. We don't know which. And it could be both. But one of these is blue. Remaining digits in box. Remaining digits in box 1 are 2, 3, 4, 5, 6. And this is negative 2. So this has to be one shaded, one unshaded, and one shaded. This is negative 3. Again, has to be one unshaded, one shaded. Negative 1 is the same. One unshaded, one shaded. Because we know these are positive digits. So that's why negative 1 has to be... This could actually be a 1-2 pair. So we don't know anything about that. Rest of box 6 are 2, 3, 4, 5, 6. Yeah, any negative 1 for 2 digits, or any negative 2, sorry, any 1s or 2s in a cage for 2 digits must be a split. And we know that for certain. So this has to be split, this has to be split. We know these are all split. This is split. Split here, this is split here. That's a 1. This 1 has to be split. Okay, so one of these is blue. This is split here because 1 always has to be split. So this must be green going this way. And this must be blue going this way. So this is blue going this way. We know at least one of these is blue, so this has to be a blue at least. And this could be blue because it can only swap once. This is split. This is 1. Negative 3 could be here and could be the same. Negative 2 is split. Negative 1 is split. Negative 1, we don't know about that. These 3 digits minus this digit is 1. So obvious, this could be... So these add up to 7 at least, and it could be up to 10. So this is 6 through 9 there. Oh, these are the same shading, because it adds up to 13. So this is the same shading. Negative 1 is split, negative 1 is split. Can you have 3 digits here with 1 there? 9 minus 6 is possible to be 3. So it could be that way. This is blue because we have all, this 2 by 2 area is all green. So these are boundaries. These are boundaries. 23 again, you have to have 3 unshaded and 1 shaded. Oh, this is green, so this must be blue here. This blue must go out here, so that's blue that way. So this is blocked. At least one of these two is green. If this were a blue, you would have a cross blue here, and you'd have a cross green here. And that pattern is not allowed in yin-yang shading, because try to connect the greens orthogonally. You have to block the blues into two areas then, which is not allowed. So this cannot be blue, it has to be green. So this is green. Therefore that's a boundary. We don't know anything about that. Okay, these two digits add up to 14. It's either 5, 9, or 6, 8. We're guaranteed one of these is 8 or 9. And with this being 7, 8, or 9, only one of these could be 8 or 9 here. So this has to be 8 or 9 here. This is obviously 7, and the remaining digits in row 1 cannot be 7, 8, or 9. So we have 1 through 6 here. 1 through 6. This can't be 5. To add up to 10, it's 4, 6, 7, 8, or 9 here. This is split, this is split, this is split. This is negative. So this has to be at least 6 greater than this digit, because it would be 1 minus 7 is negative 6, 2 minus 8. So this is 7, 8, and 9. This is 1, 2, or 3. These two digits add up to 13. 4, 9, 6, 8, or 5, 7. Sorry, 4, 9, 5, 8, or 6, 7 are the possibilities there. To add up to 13, again, you have 4, 9, 5, 8, or 6, 7. And that's in the positive and the negative way. This must be 1 away from 2, 3, 4, 5, or 6. So this is 1 through 7 here. This could be any combination. This is 1 away from each other, but that could be any combination. Can this be... This could be green and blue if this is 9 and that's 1. That's certainly possible. Yeah. Excuse me. This is positive. This is positive, so it has to be 7, 8, or 9 here. Because it's 7, 8, and 9 adds up to 24, and then you subtract the 1, which gives you 23. So this is guaranteed 7, 8, 9. In this box, we have a 7, 8, 9 guaranteed here, right? 4, 9, 5, 8, 6, or 7 add up to 13. This is 7, 8, 9 to get the negative 6. So we have 3, 7, 8, 9s already accounted for in box 6, which eliminates 7, 8, 9 in the rest of the box. This can't be 7, 8, or 9. It's a 6. So this can't be 6 or 7 here. To add up to 7 minus 6, which gives you 1, it's 1, 2, and 4, which eliminates 1, 2, 4 in the rest of the box. This can't be 1 or 2. It's 3. This can't be 4, 9. It's 5, 8. And this 3 with negative 9 gives you negative 6. So this is 9 here. And this must be 7 then. 3 eliminates 3 as a possibility here. Where is 3 in box 1? It cannot be in these cells, so it must be in this negative 2 cage. Well, negative 3 and what digit gives you negative 2 if they subtract from each other, or gives you an absolute value of 2? It has to be 3 and 5. And 5 is greater than 3, so the 5 has to be the negative. So this is 5, that's 3. That eliminates 5 in the rest of the column. That leaves the remaining digits in column 3 as 1, 5, and 8. And again, 5 cannot appear in this 23 cage. It's negative 1 with 7, 8, and 9. This 6 eliminates 6, 7 here. This 9 eliminates 4, 9 here. So this is a 5, 8 pair, which eliminates 5 and 8 in the rest of the box. And the rest of the row. This is guaranteed to be 1 here, so this cannot be 1 and 2 added together. So this must be a subtraction. So this is blue. Okay, remaining digits. 1 cannot be here because of 1 in the column. 5 eliminates 5 here. So this is 8 and 5. 8 eliminates 8 here. So remaining digits in column 2. We have 2, 3, 4, 7, 9 as possibilities. Well, to give you negative 3, this can't be 1 because 1 is guaranteed to be here. What are the remaining digits in column 1? We have 2, 4, 6 guaranteed, and 7 or 9. Well, 9 cannot be in the positive for any of the negative cages. So this cannot be 9, this can't be 9. 7 cannot be in the positive value for the negative cages because it would be 7 and 9 to get negative 2, but you can't get negative 3. And 7 and 9 also gives you negative 2, which can't give you negative 1. So this is 2, 4, or 6 here. 2 cannot be in the negative here. For the negative 3, it's at least, it has to be 7 or 9, right? 4 has at minimum a 2 positive here. So 2 minus 4 is negative 2 only, which doesn't work. And then obviously 6 minus 4 is a positive value. So this is guaranteed to be 7 and 9, which eliminates 7, 9 in the rest of the column. So 3 has to be one of these two. To get negative 3, it cannot be 2 here. It's 4 minus 7 or 6 minus 9. To get negative 1 without the... So this can't be 6 then. This can't be 4. This has to be 2 and negative 3. So this is 2 and 3, which eliminates 2 and 3 in the rest of the box. This can't be 2. This is 4, which makes this 2. So this cannot be 2 here. This is a 1, 4 pair, which eliminates 1 and 4 in the rest of the column. So it can't be 4. This is 6, which makes this 9 to be negative 3. And this must be 7 then and 4 to subtract 3. 7 eliminates 7 here. This must be 7 there. None of these can be 6. So one of these digits here is a 6. This cannot have a 4. You can't have a 3 here. This 7 eliminates 7 here. Oh, this is a negative digit, so it cannot be 1. So one of these two is a 7 here. Hmm. Hmm. Okay. This is one different. Still could be any of those combinations. If this can't be 7 anymore. For -1, you could have 1 with 2, 5 with 6, 8 with 9. So in each of these cases, this has to be the smaller digit, I think, right? 1 cannot be greater than another digit to give you -1. 5 would have to be with 4 if it's negative. Oh, wait, so this is. Yeah, to be the positive digit here, 5 would have to be. Wait. Yeah, 5 would have to be with 4, but it can't be. And 8, to be the positive digit, would have to be with 7, which it can't be. So this is always the negative digit. This is always positive then. And since this is a 2 by 2 with all negative numbers, this must be positive. This must be positive. So these are boundaries. Boundary. We have a diagonal crossing here and here, which forces both of these to be positive. Right? Because if this, again, you can't have diagonal here negative and diagonal here positive, because then to connect, you would have to break the other set into 2 distinct regions, which is not allowed. So this is positive, positive, so this is 8, cannot be 1, this is 9, and this must be 1 as a negative digit. We have a 2 by 2, which has 3 negatives, so this must be positive, which makes this negative. Oh, that's not good. That's very bad. That's very bad. Huh. That doesn't work. Huh. Did I mess up somewhere? I must have messed up somewhere. Yeah, because that's a deadly pattern in yin-yang shading. That makes this negative. It's 2 by 2, so this is positive, which makes that negative because, yeah. Shoot. Where did I mess up? This logic is still all very sound. Maybe here? Um, hmm. Dang it. No, this is still the same. Then this has to be green in some way. Yeah, you can't have 2 greens here, because if this is 2 greens and this is blue, so this has to be green here, which makes that 9. So this becomes a 1-8 pair, which eliminates 1 and 8 in the rest of the row. This cannot be 8. This is 1 and 8 here, which forces this to be 5. Oh, that works. 5 and... Oh, I had it backwards. Yeah, I had it backwards. This has to be the lesser value, so it's positive. Right. Okay. Huh. Weird. Okay, so I messed that up. I don't know why. This is 6, no 5 and 6. So where is the 6 in box 6? It has to be here. So this is 6. No 5 and 6 here. This is 2 and 3. Next to, it cannot be. We can't have 1 here. So this is a 2, 3 pair. Therefore, this can't be 2 here because the difference, if you have a 2 here, you have to have a 3 here. And that would eliminate all possibilities for this cell. So 2 has to be one of these two. Remaining digit here is a 9. So this cannot be 9 here. This can't be 4. It can't be 9 and 1 here. This is a 1-8 pair. This 9 eliminates 4 and 9 here, so this is a 6-7 pair. There's a difference of 1 here, so this is 1, 2, 3, 4. Well, this can't be 2 or 3. If this is 1, that doesn't subtract with any other digit to give you a value of 1. So this must be 4, and this must be 3, which makes this a 1-2 pair. 1 and 2 is only 1 and 3 would work here. 2 and 4 has to work here. This can't be 3, so this must be 4. So this must be 4 and 2. 4 is the blue as the negative, which is the higher digit. That's green. This can't be 2. This is 1. This must have a difference of 3, or it cannot be 1 and 2. So this has to have a difference of 3. So this is green, and this is a boundary here. It has to be 3 and 6. And the larger value is negative, so that's 6, 3, which makes this 4. That eliminates 4 from being here. This can't be 3. We have 1, 4, and 6 here. Remaining digit is a 5. Okay, so we have to figure out some way to get this to add up to 6 with the negatives. 4 eliminates 4 here, so that's 1 and 4. Remaining digits in row 8, we have 1, 2, and 7. Remaining digits in row 9, we have 5, 8, and 9. Can this ever add up to 8? And the answer is no. We don't have 1 and 7, no 2 and 6, no 3 and 5. So this must be subtracting to 8. Obviously, this can't add to 8, so this is subtracting to 3. So this must be 9 and 1 here. Difference of 1 then is 8 and 7, which makes this 5 and 2. 7 eliminates 7 here, so it's 9. This 8 eliminates 8 here, so it's 1, and that's 8. 1 is the only positive in that region, so we've swapped then, so this is green. This is all green here, and this is a boundary. 9 eliminates 9 here, so it's 7. 5 eliminates 5 here, so it's 4. This is the positive, and this must be the negative. So this is blue. This cannot be, it has to be 5. That means this can't be 5 or 6 here, or 1. This is a 2, 3, 4 triplet. No 2, 3, 4, or 5, so this is 1 or 6. This must be blue because of the 2x2 area that's all green. And this must get you -3. It must be 1, 2, and 3, and 9. So this is 1, 2, 3, which makes this 4 and 9. This must be 4 and 6. It's -2. Oh, we should have had a boundary there too. This is blue. This is 2 and 3. 1 eliminates 1 here. 9 eliminates 9 here. So this is 8. This is 9. This cannot be 5 and 9 anymore. It's 6 and 8, which eliminates 6 and 8 in the rest of the row. So this cannot be 6 and 8. So this can't be 4. Well, we have a 2, 3, 4 triplet, which eliminates 2, 3, 4 in the rest of the row 1. So this can't be 2, 3, or 4. This is 5. This can't be 8 because of 8 in the row. Can't be 2 and 8. Can't be 4 here, so this is 3 and 7 to add up to 10. That 7 eliminates 7 here, so it's 6 and 7. This 6 eliminates 6 here, so it's 8 and 6. This can't be 5. Okay, this is boundary. 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 Okay. This is -9, and oh, anything that adds up to 9 would have to be the same set. So this is both blue. Cannot be 1, 8, cannot be 2, 7, so it's 3, 6, which it can't be because of 6 in the columns. So it has to be 4, 5. That eliminates 4 and 5 in the rest of the row. So we have 2, 3, and 6 here. This can't be 3 because, or 6 because of 3 and 6 in the box. So this 3 eliminates 3 here, so it's 2 and 3. 2 eliminates 2 here, so it's 4 and 5. And we have this adds up to 9. 2 and 6 adds up to 8. So 9 minus 8 would be 1. This is 2, that's 6. This can't be 4, 6, that's 2. So these both must be blue. We have a 2 by 2 area that's all blue for 3 cells, so this must be green. Boundary, boundary. Okay, this is -12. That's interesting. 4 eliminates 4 here, so this is 5. That leaves that as a 7. 5 eliminates 5 here, so it's 4. 5 eliminates 5 here, so it's 8 and 5. Remaining digits in column 5 are 1 and 8. They must add up to 9, so both of these are green. We have a 1, 8, 1, 8 pair in row 4, which eliminates 1 and 8 in the rest of the row. That leaves the remaining digits as 2, 3, and 7. Well, this can't be 7 because of 7 in the box, so this is 2 and 3. That leaves this as a 7. This must be 1 and 8 because of the remaining digits in the column, and this must be 9. Okay, so then we have to have some combination here, which will add up to -1. Okay, and this is 2 by 2 area that's all blue for 3 cells, so this must be green. 9 then definitely has to be negative. If it's not, then the problem is, yeah. Then you would have this adding up to 16, and you have a -5 at best here. So therefore, this is negative. The green has to connect out to the rest of the green regions, so this is green. If we try to have another green here, that doesn't work. Sorry, these are both blue because it's 8 and 7, giving you negative. We need to do this. Okay, so I think this has to be 3, 7, subtracting out 2 and 9. If you have 2, 3, and 7 be positive, that's 12 minus 9 is not -1. So this must be 3 here and 2 here. This is 2 and 3, not 6. 2 and 3. 10 minus 11 is -1, so that works. 3 is a larger number and it's negative, so this must be blue, which makes this green. Uh, 1, 5, 4, 6 to get to 6. I think it's 6 and 5 minus 1 and 4, right? 6 and 4 minus 1 and 5 would give you 4 in value. 6, 4, and 1 is 11. Oh, that could work too. At least 1 out of 1 and 4 is positive. So it cannot be two negatives here. So it cannot be 6, 5 minus 1 and 4. So one of these is positive, so both must be positive. So it must be 1, 6, and 4 gives you green. Therefore, this is blue, which means we have a 2 by 2 area. That's 3 blues. So this must be green also. This is a cross of blue, so this cannot be blue here. This cannot be green here because then we'd have the deadly cross. So this is blue, which makes that a 1, which makes this 8. 1, 8, 1, and that's 8. This is green. We need to continue this to have boundaries. Blue, oops. That's done. This is a boundary. This must connect to the blues. So that has to connect one way or the other. This is 1, this is 8. If we have to have -7 and -8. So this is blue. So -7, -8 is 15. Plus 3 is -12. And that's satisfied that way. Oh, and we forgot about the boundary around the edge. And this is boundary. So that makes that an 8. An 8. We'll eventually get there. Yeah, interesting little puzzle. I missed a line here. Very restrictive with the sums, but you have to be able to make this solvable, right? Once you start introducing negative values, that opens up a wide variety of that opens up a lot of things that you are usually restricted on. So, yeah. You need those really strong restrictions to basically be able to make this solvable. Otherwise, it becomes very, very difficult very quickly. Pretty cool, pretty cool. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.